last week, we just mentioned the eigenvalues and eigenvectors. We can have a matrix times a vector, and then I can convert, or this can be expressed into a constant lambda times your vector. This constant value will be called eigenvalue, and the x will be called eigenvector. And we know that eigenvectors cannot be zero. Otherwise, it is obvious. But your eigenvalue could be zero. Okay, this example just show you that the eigenvalue is zero. So matrix A times x can be equal to just 0 times this vector. And here are some properties. One of the applications is to find the power of a matrix. Okay, to find the power of a matrix, this is called a Cayley-Hamilton theory. If you want to find, for example, a to the n, okay, using the characteristic equations. For characteristic equations, where is that? So once you have a minus lambda I, this determinant equal to 0, then I have the characteristic polynomial. When this is equal to 0, that is the characteristic equation. Now, let's just compute a to the m. Suppose we know the matrix is A. So first, we need to find their characteristic equation, and of course, their eigenvalue. So the characteristic equation a minus lambda I, and take the determinant equal to 0. So you minus lambda, minus lambda, minus lambda, and take the determinant. You will get minus lambda cubed plus 2 lambda squared plus lambda minus 2 equals 0. Then you have 3 roots for lambda. Lambda 1 minus 1, lambda 2 1, and lambda 3 2. Make sure that you know how to find your characteristic equations, and of course how do you find the root. Then according to this equation, we have this matrix to the m will be C naught I plus C1 A and C2 A squared. And lambda to the m will be C naught plus C1 lambda plus C2 lambda squared. So now you can bring minus 1, 1, 2 here. So when lambda is lambda 1, that means minus 1 to the m, it will be equal to C naught minus C1 plus C2. And 1 to the m will be C naught plus C1 plus C2. And 2 to the m, C naught plus 2C1 plus 4C2. Therefore, you can get a C naught Okay, this is for C0, C1, and C2. And then you can bring it back to your matrix A to the M. Then you'll get A to the M. Wait. 1/6, 9 minus 2 to the M plus 1 minus minus 1 to the M. 1 minus 2 to the M. 1/6, 3 minus 2 to the M minus 1 minus minus 1 and 1/3 2 to the M 1/3 2 to the M minus minus 1 to the M. Right. This is one way to find the power of matrix. And later on, we will also use another method to find that. And you can compare it, which one is more straightforward or which one is easier. Okay. Next, we're going to talk about the diagonalization. So what is diagonalization? First, we need to define what is a diagonal matrix. Okay, this is the common expression for the matrix, right? The element with brackets. And we call this is a diagonal matrix if I is not equal to j, that should be that is 0, which means of diagonal element is 0. So here we call this diagonal part, this is the main diagonal element. Diagonal. And the off diagonal parts is 0, which is here. This is off diagonal elements. All right. So now this is a diagonal matrix. I only have values in the main diagonal elements. Others will be all zeros. Okay. And then for this diagonal matrix, we have some properties. If I have two diagonal matrices, then D times W, or W product D, you don't need to calculate. You only need to multiply your diagonal elements in each position. So others will be still 0, which means after you do the product, this matrix is still a diagonal matrix. Okay, so because the off diagonal elements are still zeros. And then for the main diagonal elements, they have values. Okay, and their values is the multiplication of each corresponding element in their matrix. The second one, if I take the determinant, since they're all 0, right? If I choose the first row, I get D1 and times the rest. D1 times the rest, right? And others will be 0, so you don't need to calculate. Then for this sub-matrix, you also choose the first column. Then I have D2 times the rest, because others will be all 0. So that's why for the determinant, you can see that here it will be your elements from on the main diagonal and make it multiplication, D1 to Dn. Okay? And we say D is non-singular if and only if the main diagonal element is non-zero. What is non-singular and singular? If I say the matrix is singular, that means the matrix I have at least one row, they are all zeros. It is called singular. And for non-singular, they say only if the main diagonal element is non-zero, all non-zero. Because I can also say that this is diagonal matrix. Here is 0, but I only have values in the main diagonal elements. Others are all 0. This is also called a diagonal matrix. But this is not non-singular. It is singular because the last row is all zeros. Singular means that I cannot find the inverse matrix. Okay. So for non-singular, I have a inverse, and then for all the elements in main diagonal, they should have some values. They cannot have a 0. Once they have a 0, even though here, that means in that row they are all zeros. If you have all zeros in a row, then you cannot find an inverse matrix, which also means that it is singular. It is not non-singular. Okay. So since I have values in the main diagonal element, then I can get my inverse. What is the inverse? The inverse matrix is still a diagonal matrix. You see that the diagonal part are all zeros. For the main diagonal part, they just 1 over their value. 1 over D1, 1 over D2 to 1 over Dn. All right. So you also don't need to calculate the inverse because it's just that you reciprocal of your value. Okay. Then for this diagonal matrix D, I have eigenvalues, and the eigenvalues are just the main diagonal element, D1 to Dn. You don't need to calculate that again, because for this example, D1 minus lambda, D2 minus lambda to minus lambda, and you take the determinant. When you take the determinant, what do you have? D1 minus lambda, D2 minus lambda times Dn minus lambda, that should be 0. Then your lambda should be D1, D2 to Dn. Okay? Alright, so now we know the diagonal matrix. Then let's see what is diagonalization, or we may say that a matrix A is diagonalizable. And what does that mean? Matrix A, n by n, square matrix, we say A is diagonalizable if and only if I can find or there exists in P. It is still n by n matrix P. Then P inverse A times P is a diagonal matrix. Then in that case, we can say that P diagonalizes A. Okay. For example, if I have a matrix A, let me give you 2 minutes. Please find the eigenvalue. If I have a matrix A, then what is the eigenvalue for matrix A? So I have -1 and 3. So suppose 1 is -1. What is the eigenvector? Well, for the rest of the semester, then you need to find eigenvalue and eigenvectors all the time. Okay, so make sure that you know how to find your eigenvalue and also their corresponding eigenvector. Okay, so now it's -1. So -1 -1. This matrix times x1, x2 should be 0. And then you can find x1 and x2. That will be your eigenvector. It's 1, 0. And when eigenvalue is 3, what is your eigenvector? Let's try this, right? Try to find this eigenvector. Yes. 1 and 1. So you get 1 and 1. Now, for this P, you can see that A is not a diagonal matrix, right? Because I have values of a diagonal element. Now, but I may say that A is diagonalizable. If and only if I can get a matrix P, then P inverse AP will be equal to a diagonal matrix. Then we say P diagonalizes A. So now if I choose P, (1, 0, 1, 1), then what is the P inverse? The P inverse, that will be 1, 0, -1, 1. Then for this P, you can try P inverse A, P, 1, 0, -1, 1. A is -1, 0, 4, 3. And 1, 0, 1, 1. Then they give you -1, 0, and 0, 3. This gives you a diagonal matrix. Then we can say this matrix P diagonalizes A. And matrix A in this case is diagonalizable. Okay. Any questions? And then from this example, what do you observe? What do you observe about the matrix P? And also the diagonal matrix. Anyone, any thought? Based on this example, we found the P matrix and also the diagonal matrix. And what did you observe for these two matrices? Any guess? First, how about this matrix P? A matrix P is 1, 0, 0, 1, 0, 1, 1. Did you observe anything here? No? When matrix A is here, we found the eigenvalues and their corresponding eigenvectors, corresponding eigenvectors. And you see that those are just the eigenvectors. I put eigenvectors together to form this matrix P. Right? And then once they do the P inverse AP to get the diagonal matrix, here's a diagonal matrix. And you can see -1 and 3. Their values are just the eigenvalues. Okay. So that means if you can find the eigenvectors, then to form this P using all the eigenvectors, then you can diagonalize this A, and the diagonal matrix, you just put their eigenvalues. All right. Any questions so far? Then if I have a non-zero multiple of an eigenvector, so it's 1 0 and 1 1. Now suppose I have 3 0 and 2 2. This times 3 and this times 2. Then I form this matrix Q. So Q is 3 0 2 2. Let's see. The Q inverse be 1/3 0 1/3 1/2. Then Q inverse A Q if I use Q, then Q inverse AQ will be -1 0 0 3. Q also diagonalizes A, right? Because the final answer here is a diagonal matrix. Any questions here? So that should give you the concept that once you have eigenvalues are fixed, but for your corresponding eigenvector, some people may get here is 2 0 or 4 0, or here the other person may get like 1 1/2 1/2 or even -1 -1. It doesn't matter for your eigenvectors. Once you have a correct eigenvalues, then you use your corresponding eigenvectors to form the matrix. Then that matrix can diagonalize this A. And when they diagonalize this A, the diagonal matrix, no matter what your Q or P or this matrix are, the answer will be always your eigenvalues on the main diagonal elements. Okay? Then let me ask you, if I have a matrix S, it's 1, 1, 1, 0, then what is S inverse A S? Anyone? Yes. Say louder. 3, 0, 0, -1. Okay, so you don't need to calculate. Actually, you should immediately know that it should be 3, 0, 0, -1. Because now, observe, if I have a P 1, 0, 1, 0, 1, 1, 1, 0, the eigenvector, the corresponding eigenvalue is -1. So they put, since they are in the first column, so here the first one is -1. Second one, 1, 1, the eigenvector. Their eigenvalue is 3. So for this position, it should be 3. So if I switch this order, 1, 1, their corresponding eigenvalue is 3. So they should put 3 first. 1, 0, their corresponding eigenvalue is -1. Okay, so here I change the order of eigenvector. And then for the diagonal matrix, the order of eigenvalue changes. Okay, because they switch, and then they should also switch. Any questions for this diagonalization? This is very important because later on we will use this a lot, and you will also see something interesting later. All right. If you don't have any questions, then based on this concept, I have a matrix A n by n, and also I have eigenvectors v1 to vn with their corresponding eigenvalues lambda 1, lambda 2 to lambda n. Now, suppose my eigenvectors are linear independent. So since it is linear independent, the P is non-singular. And then P inverse A P. This matrix will be lambda 1, lambda 2 to lambda n. And of diagonal, that's 0. And this is a diagonal matrix. Diagonal matrix D. For this diagonal matrix, well, P inverse AP equals D. In other ways, I can express A as P D P inverse. That is called the eigenvector eigenvalue decomposition. Eigenvector eigenvalue decomposition of matrix A. Okay. Any questions for this? Now let's see. If you don't have any questions, let's practice this one. A, this matrix. Again, first you need to find the eigenvalue. For this matrix, what are the eigenvalues? 3 by 3. I should expect 3 eigenvalues. So again, let me give you two minutes. If you found the eigenvalues, just shout it out loud. Yes. Okay. So there'll be 1, -1, and -2. Okay, so now you know the eigenvalues are 1, -1, and -2. Please find your own eigenvectors. 1, -1, and -2. What are the eigenvectors for each corresponding eigenvalues? I have eigenvalue 1. So you should have an eigenvector, and then also when eigenvalue is -1, and then eigenvalue is 2, -2. What is the eigenvector? For 1 is 0, 1, 0, 1, 0, 0, 5, 0, -1. Okay. For other people, you may find 0, 2, 0, 3, 0, 0, 10, 0, -2. That's fine. Okay. So for the eigenvalue and eigenvector, if I can find the eigenvalue and eigenvectors, and you can also check those eigenvectors are linearly independent, then I can form the matrix P. For the matrix P, I have 0, 1, 0, 1, 0, 0, 5, 0, -1. And you can see this is corresponding for, this is eigenvalue 1. Second column, -1, and -2 for the third column. And the P inverse, you can do it by yourself or just at home. Then your P inverse A P is what? Since the first column you use 1, okay, well, you used the eigenvector with the corresponding eigenvalue 1, so here you should get 1, 0, 0, and the second column, that's -1, so -1, and 0, 0, and the last will be 0, 0, -2. Okay. Any questions for this one? All right, let's continue. So far, it looks like everything goes smoothly. I have eigenvalues, and then I can find the eigenvectors, right? But what if I have the same eigenvalues, which means I have a repeated eigenvalues? Then you should have a lot of questions. First is like, how can I find the eigenvectors? Right. And if I have the same eigenvalues, how can I write this diagonal matrix? So first, let's see. If I have a matrix A, then you can find the eigenvalues are 1, 1, and -3. So when number is -3, that's just a typical eigenvalues, and then you know you can find eigenvector without any questions. 1, 3, 1. But how about eigenvalues equals 1? When eigenvalue equals 1, then we need to find the eigenvector. So first, let's see. A minus lambda. So 4, 12, 4. Minus 4, minus 12, minus 4. And 4, 12, 4. There should be 0. Then what is x1, x2, and x3? It looks like it is x1 minus x2 plus x3 equals 0, right? How do you determine x1, x2, and x3? The general solution second, x1 minus x2 plus x3 equals 0. So if I have alpha and beta, then your x3 will be beta minus alpha, right? So I should have alpha, beta, beta minus alpha. Then we can choose, say, alpha equals 1, beta equals 0. In this case, we have 1, 0 minus 1. We can also choose alpha equals 0, beta equals 1. Then we have 0, 1, 1. To find the matrix P that can diagonalize A, my P should be non-singular. This matrix is non-singular. That means for the eigenvectors, those eigenvectors should be linearly independent. So if those eigenvectors are linearly independent, then okay, I can form this P, which can diagonalize A. So if I choose these two vectors, then we need to check if they are linearly independent. And they did. For these two, they are linearly independent. So we have three vectors. We have 1, 3, 1, that is the eigenvalue minus 3. The corresponding eigenvector, it will be 1, 3, 1. And then 1, 1, 0, minus 1, and also 0, 1, 1. Those three are linearly independent. So my matrix P 1, 3, 1, 1, 0, minus 1, 0, 1, 1. And then P inverse AP. Can someone tell me the answer for this matrix, P inverse AP? The first column is the eigenvector with corresponding eigenvalue minus 3. So minus 3, 0, 0. The second one, the corresponding eigenvalue 1. So 0, 1, 0. The last column, same thing. The eigenvalue is 1. 0, 0, 1. Okay? Any questions? Any thoughts? If you don't have any questions, then I ask you the question. If we have repeated eigenvalues, okay, then we try to find different eigenvectors. Then you should ask this question, right? What if I cannot find those two eigenvalues? They are linearly independent. What should we do? If I have repeated eigenvalues, but I can only find one eigenvector. How can I find the other one? You can think about these questions, okay? Now, next, we know that A, this matrix is a diagonalizable matrix. And A has n linearly independent eigenvectors. So Q inverse AQ is a diagonal matrix. The diagonal element, just the eigenvalues of A. And the columns of Q will be the corresponding eigenvectors. This is kind of like a wrap up of what we just learned. Okay. So suppose they say if Q inverse AQ is a diagonal matrix, suppose Q inverse AQ is a diagonal matrix, let's say D1, 0, D2, 2, Dn. And also the Vj, this column, this is the column J of the matrix Q. So the matrix Q, this one is column J. Now I have a V1, V2 to Vn, and those are linearly independent. V1, V2 to Vn are linearly independent. If they are linearly independent, well, And also they are linearly independent because Q, this matrix, is non-singular. And then Q inverse AQ will be the diagonal matrix D. This is diagonal matrix D. And this, if you times Q on the left hand side, here I also times Q. This becomes identity matrix. So AQ equals QD. Okay? What is QD? Your Q is V1, V2 to Vn. V is a column vector times D. Remember, D is a diagonal matrix. D1, D2 to Dn. There are others, they are all zeros. So when they times the diagonal matrix D, I only have V1 times D1. And others will be 0 times V2 to 0 times Vn. So later on, you get D1, V1, D2, V2, till Dn, Vn. So here, we have dj, vj. D is a scalar and v is a vector. So dj, vj, they'll be in the jth column. This is right hand side. Now let's investigate the left hand side. What is AQ? For AQ, you'll get A V1, A V2, till A Vn. And your A times Vj is in the jth column. And since they are equal, so they should be equal. Okay. So since AQ equals QD, then AVJ equals DVJ. See? A times a matrix times a vector becomes a scalar times a vector. So DJ is the eigenvalue, and the VJ is the associated eigenvector. So dj is an eigenvalue. With their corresponding eigenvector Vj. All right, any questions for this? Overall, it's like if I can have a matrix that diagonalizes a matrix A, that matrix is formed by the eigenvectors of the matrix A. And also, when it diagonalizes A, the final diagonal matrix is composed by the eigenvalues. All right. Any questions for this one? We will use these concepts to solve the system differential equations later. Okay, they'll be in a week. Right. But before that, we still have a small part of this, some concept that you should know, and you should know some different spatial matrices. And now we are going to talk about those matrices. Okay. The first one is orthogonal matrices. Make sure that you know the definition of each matrix, because later on, once we said now we need to use symmetric matrix, for example, to do something, then you should have the concept, you should have the image, what symmetric matrix looks like. Okay. And those are very important metrics that we will use in a week. First, orthogonal matrix. We say A is an orthogonal matrix if and only if here A times A transpose equals A transpose times A. And then no matter they change the order, the answer is an identity matrix. And since it is an identity matrix, that means the A inverse is A transpose, right? AAT is identity matrix. The A should be AT, should be A inverse. Okay? So if your inverse is your transpose, then this matrix is called orthogonal matrix. And which means that orthogonal matrix is non-singular because it has an inverse. Once you have an inverse matrix, this matrix is non-singular. All right. So if I want to find the inverse matrix of A, first, you don't need to be in a hurry to really solve using some methods to solve the inverse. You can observe if the transpose is if your matrix times your transpose is an identity matrix, well, then we know it is an orthogonal matrix, and we also know that the transpose will be your inverse. So we can check if this matrix itself times its transpose. So A transpose, let's see, 0, 1, 0, 1 over square root of 5, 0, 1 over square root of 5, 2 over square root of 5. Now transpose. Transpose means that the column becomes row, row becomes column. So the first row will become the first column. Second row will be the second column. Third row will be the third column. Okay. Then 0, 1 over square root of 5, 2 over square root of 5, 1, 0, 0, 0, 2 over square root of 5, minus 1 over square root of 5. Now 0. It should be identity matrix. 3 by 3. So I3. And since A times S in transpose is an identity matrix, then I don't need to calculate the inverse. The inverse is just the transpose matrix of A. Okay. And then if it is an orthogonal matrix, you can also verify that if I take the determinant, it's either be 1 or minus 1. Alright, any questions for this one? No? We will use that a lot in next chapter. Okay, so next matrix, symmetric matrix. What is symmetric matrix? If the transpose of that matrix is itself. Okay, so for example, in this case, 4 by 4, this is diagonal element. And then if I transpose the first column, the first row becomes the first column. So you can see they are equal, they are equal, 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 equal. They are equal. So it's like it is like a mirror. So this is called symmetric. This matrix is called symmetric. And you can see that for this example, I can also have a pi as an element in this matrix. So symmetric matrices do not have to have a real numbers as an element. I can also put exponential 2, but here should be exponential 2. Then they are symmetric. Alright. For the symmetric matrix, the eigenvalues of a real, if this is a real symmetric matrix, then eigenvalues are also real. If it is both 3 and 3, then the eigenvalues should be also real. How do we prove this? First, just recall the complex number. Well, even though we will also talk about the complex number in the next semester, but I think in your junior high or senior high, or even in your calculus, they mentioned that a little bit. So if I have A plus BI, then what is the Z bar? Or we say Z conjugate. Z conjugate becomes A minus BI. So here's called complex conjugate. If I conjugate again, conjugate and then conjugate, they'll back to Z. Because here, if I do the conjugate again, minus become positive or positive sign. So if you do double conjugates, then you go back to your original number. And if your z times the conjugate of itself, then this will be your magnitude squared. And then the magnitude z we will choose a squared plus b squared. Square root of a squared plus b squared. That's the magnitude. For the matrix, the conjugate of matrix C will be C bar. Then if I take the transpose, that also means I can do the transpose first and then do the conjugate, do the conjugation. All right. Any questions about the symmetric matrix so far? Here, based on this theory, if eigenvalues are real, then the symmetrics, well, if no, the symmetric matrix is a real matrix, then the eigenvalues will be also all real. Here is the example. For still like quickly recall. Here is the complex matrix. Then what is the C transpose? Row becomes column, so now I have 3 columns. I 1 minus 2i 3 0 minus 2 plus I 4. Then almost done. Let's take the conjugate. So if I conjugate, I becomes minus I. 1 minus 2i will be 1 plus 2i. Three 0. And then minus 2 plus I becomes minus 2 minus I. Now we need to check if this is correct. So now this is the conjugate and then transpose. But now I want to have a complex conjugate first and then transpose. So conjugate we have minus I, minus 2 minus I, and here is 1 plus 2I, 0, 4. And now I can transpose it. Yep, so we transpose. The first row becomes the first column. Minus I, 1 plus 2I. Minus 2 minus I, 4. And you see that they are the same. Any questions for this one? Here's a note. If I want to do the conjugation, I can do the product first and then conjugate. And I can also do the conjugation first and then do the product. So here means conjugate of a product will be equal to the product of the conjugate. What does that mean, a conjugation or conjugate? So if we draw a coordinate, here is AB. AB means A plus BI. And then the conjugate means it's kind of like a mirror. So they project to here. A minus B. It's like a reflection. Reflection across the horizontal axis. Alright, so now we are going to prove the theory. So the eigenvalues of a real symmetric matrix are real. If you have a real symmetric matrix, then the eigenvalue should be also real. So how do we prove this? So here is the proof. Let's have an m by m matrix A. And this is a real symmetric matrix. And we have a eigenvalue lambda. Then we want to show lambda is real. I have an eigenvalue, right? Then I should have a corresponding eigenvector. So that's that. The eigenvector E, that's E1 to En. This is the eigenvector. So since it is a corresponding eigenvector, then we know A times the vector E should be lambda times E. Right? So far so good. Now we are multiplying a common term from both sides. So let's times conjugate transpose. So conjugate transpose lambda E. So here, what is the conjugate and transpose? We know E is this one, right? E1 to En. If I take the conjugate, then I have O conjugate. And transpose, column becomes row. So conjugate and transpose becomes E1, E2, to En and since this is a constant, right? So this is constant, I can put the outside. This becomes lambda E transpose conjugate and then times E. So you have this times E, E1, E2 to En. Right, let's write it down. It should be lambda E1, E2 to En, their own conjugate, times E1, E2 to En. It should be lambda E1 E plus E2 conjugate E2 till En conjugate times En. And for this part, they are real number. Okay. Now, since this is a real number, then I can take the conjugate. Here I can take the conjugate. So when I take the conjugate, right, one more. Let's write this first. E, T, A, E. When I take the conjugate, let's use maybe blue. Conjugate of product will be equal to the product of the conjugate. So here I can change that to the product of a conjugate. That means each one I take the conjugate. And A, E, and then this is also the product. Okay, so the conjugate of product, it will be equal to the product of the conjugate. So I have this conjugate and also A conjugate and E conjugate. And this is equal to e to the t, E conjugate times A and E. If you do the double conjugate, they just cancel it out. And then the difference is that A conjugate, this matches, if I do the conjugate, it's the same. Because we assume that this matrix is a real matrix, real symmetric matrix. Because if I take the conjugate, they'll be the same because it is a real matrix. Then this part, I can also think about this part as e to the t, no, E transpose. I can also do the transpose. They will be the same. Why? Because E transpose times A times the conjugate of E is actually, this is 1 by 1 matrix. So when I take the transpose, it doesn't matter. You can verify that this finally will be like 1 by 1 matrix, just like a number. So if I take the transpose, that means when you do the transpose, I will do that backwards. This first and then go back. Okay, so this will be this transpose times A transpose times E to the T transpose. If I have a transpose and then transpose, they're back to its original one. So T A transpose E. And A transpose, A is a symmetric matrix, so it is A E. All right, done.